In today's class, we'll be discussing about how to construct a DFA from. Now, as it is mentioned in this slide, so main focus of this class will be the recap of the previous class where we had discussed about how an NFA can be constructed from regular expressions. We'll be studying about some certain operations like epsilon closure of T, where T is a set of states and conversion from N to DF. So, while studying the construction of NFA from regular expression, you have studied some rules where you got to know how to construct NFA when there is the operation involved in regular expression, where concatenation operation involved in the and where a clean closure operations involved in the regular. And ultimately, we'll be studying how same NFA can be converted or determined. So here we'll be studying about basically one algorithm by which you convert NFA to DFA. So the input of this algorithm will be an NFA, given NFA, which will be assuming that has been constructed for expression. And the output will be the equivalent DFA, D, which is D, and that will accept the same language as it is. And the the constructed DFA will be noted in terms of a transition. Now, there are certain basic operations that you are supposed to know for going to that. One is your epsilon closure of T, and epsilon closure of S is a single state, where S is a single state. Considering the description of this operation will give you some set of NFS states which are reachable from the NFS state as on epsilon transition only. Whereas in case of epsilon closure of T, here we are not considering as a single state, but T is a set of states. So therefore, when we'll be constructing epsilon closure of T, we'll be constructing epsilon closure of all the states which are part of the T set, and we'll take the union of all the closure set goes for silent. Then another move of TA. The move of TA, it is the set of NFS states to which there is a transition on the input symbol A from some state S in. So therefore, here also T is a set of states. T includes a set of states, and A is a particular input. Now, these are the two algorithms which we are going to perform, for this purpose. First, you are supposed to know about the epsilon closure of T, and using this epsilon closure of T, we are going to compute the DF given. So first we'll discuss about the epsilon closure of T. As I have mentioned, this T is the set of states. So T includes multiple states, not necessarily a single state. So first we are going to push all the states which are present in T and onto a stack. Then we are going to initialize we have epsilon closure of T as the states which are part of T. Then we are going to use a while loop where we are going to check, we are going to the operation as long as stack is not empty. As stack is initiated holding all the states which are part of T, we are going to pop out to perform pop operations. Means we will get therefore the topmost state which was pushed in stack, and we are going to perform for each state U with an age from the popped out state T to U have a epsilon as an input. We are going to take if U on that particular state, if it is not present in the epsilon closure of T, add that state into epsilon. And then if it is not present, we are going to push it into the stack again. And once this is done, once you are understand So initially epsilon closure of S naught, the initial state, is the only state in the D state. In a D state, we have all the state, which will be the state for the constructed. Okay, that's why the initial epsilon closure of S naught is the only state in the, and it will be unmarked, considered unmarked. Now, thus, if there is an unmarked state T in D state, so initially the unmarked state will be the epsilon, then we are going to mark it as T. We are going to mark that state. And after that, we are going to use a for loop for each input symbol. Because the input symbol, whatever input symbol was there for the NFA, the same, we are going to, both are going to be considered as an equivalent machine accepting the same language. For each input A, we are going to perform this epsilon closure or move of A, and which will be the output is a new state is coming, then we'll put it U, and if that U is not present in the D state, we are going to add that U as an unmarked state in the D state. We're going to add the transition, the transition table as D tran T of A, because T which was marked, and we're going to take an example. Suppose this is the NFA that has been constructed from a regular expression. Now for this one, we do the DF. Initially, as you have seen earlier, we are going to epsilon S naught. Epsilon closure of S naught, epsilon closure operation forming. So as for this one, what we are doing, we are consider all the states which we can reach from tag data. So therefore, 0 from epsilon closure of 0, where 0 is the, okay? So you can reach 0, one state, then we can reach 1 epsilon transition, we can reach 2, 4, we can reach 7, and this state is in the present, which will be given as, which will be which will be added into the D. So therefore, now, and the input symbol that we are going to be, because it okay. So thus our first step is to mark this E. Mark this E states and compute. Therefore, next we are going to compute the tran A0, which is equal to epsilon closure of move of. And similarly, we are going to compute the tran of A comma B for the input symbol B, and it will be computed as epsilon closure move of. Move of AA means we are going to consider move of all the states which are part of A, that is 0, 1, 2, 4, 5. 0, 1, 2, 4, 4, 5, 0, 1, 2, 4, 7. So among these states 0, 1, 2, 4, 7, we see move of 0, comma A. We need to consider move 1, comma A for the A input symbol. 2, comma A, similarly 4, comma A at the same time, 7, comma. Out of this, we are only able to find that only 2 and 7 have transition on A, that to also 3 and 8. So therefore, move of A B, comma A. As epsilon closure of 3, it will be because move of A we have got 3, comma 8 set of states. So I will be writing epsilon 3, 8. Which if I now we need to compute epsilon closure of 3 union epsilon closure of 8. Therefore, it will give you 1, 2, 3, 4, 6, 7, 8. So this will be a new state which is not present because earlier state was 1, 2, which is A, 0, 1, 2, 4, 7. Now new state has, we're going to give it as a new name which is as B, and it will be part of your DFA. Similarly, we'll be computing, now you'll be computing for For this B also same operation we do because it going to mark it and then going to proceed. We are going to follow the same process. Accordingly, we'll perform the same operation, and once you perform the same operation for both the inputs A comma B, you will get a transition table, something like this one, where as you have seen when A was the state and input was A, you have got B. So when you compute A and input symbol B, you will get, and accordingly you will get this transition table, which is for DFA. This is being represented by this state diagram in transition table. Transition. As you can discuss, if you can take some example for this problem also to compute epsilon closure of Q naught. This is another problem diagram I have given, and here also the state of states are Q naught, Q2. And if you compute epsilon closure of Q naught, means you are looking for all the states which you can reach from the state Q naught on epsilon transition. So by default Q naught, then and Q2 also similarly epsilon closure of Q1 is Q1, Q2, and epsilon closure of Q2 it is Q epsilon closure of Q2 it should be Q2 only. Similarly, in epsilon for this diagram, epsilon closure of 1, it will be 1, 2, 3, 4, then it will be 6. So similarly, epsilon closure of 2, 2, 3, 6. Epsilon closure of 3, you will get 3 and 6. By default, the state should come for whom you are computing epsilon closure. Epsilon closure of 4, only 4, because the other transition is 3. Epsilon closure of 5, 5, and another one 7. Epsilon closure of 6, 6, because there is no other transition from 6, which is coming out from 6. Epsilon closure of 7, this only. So I think you are able to understand how to construct a DFA from a given entity using the epsilon closure functions. And now this DFA can have, in the subsequent class, you'll study how to minimize this. This DFA will be your recognizer, which is going to decide whether a string is a valid string or a given pattern represented by. So for the references are concerned, these are the references which are followed. Have any doubt, you can always ask me.